I'd like to introduce Denise Verral. And Denise, I hope I pronounced your name correctly. But Denise is a research scientist at the Polar Research Institute, which is part of the Scientific and Technological Research Council of Turkey. She's just about completed her master's degree in geological engineering from Istanbul University. Today, she is going to talk about Thermokarst lakes and the ecological responses to change. Denise, it's all yours.
Thank you so much, Kevin. So let me share my screen. So I hope you all can see it. Perfect. Once again, thank you, Kevin and Mistia. It's an absolute pleasure to be part of a Cryosphere Seminar Series. As you know from the title, we will be talking about Thermokarst lakes and its ecological response. But firstly, we will go back to another point a little bit. So let's get started. First of all, I don't know what weather you have, but the weather is awesome here. And I want you to take this moment to just go out and look at from your window and look up if possible, please. Just to take this time for yourself and look out from your window. I hope you did. Okay, so what did you see? Maybe the wind that is moving trees, or the cloud you see dancing there, or even the sun you feel on your face are all the results of Earth's atmosphere. So let's start from here. An atmosphere is the layers of gases surrounding a planet or other celestial body. The atmosphere protects life on Earth by shielding it from incoming ultraviolet, keeping the ultraviolet radiation, keeping the planet warm through insulation, and preventing extremes between day and night temperatures. Earth's atmosphere stretches from the surface of the planet up to as far as 10,000 kilometers above. After that, the atmosphere blends into space. Not all scientists agree where the actual upper boundary of the atmosphere is, but they can agree that the bulk of the atmosphere is located close to Earth's surface, up to a distance of around 8 to 15 kilometers. While oxygen is necessary for most life on Earth, the majority of Earth's atmosphere is not only oxygen. Earth's atmosphere is composed about 28% nitrogen, 21% oxygen, 0.9% argon, and 0.1% of other gases. So we will be mainly focusing on this 0.1 other gases. Trace amounts of carbon dioxide, methane, water vapor, and neon are some of the other gases that make up the remaining 0.1%. So this will bring us to another point, which is carbon cycle. The carbon cycle is the biogeochemical cycle by which carbon is exchanged among the biosphere, pedosphere, geosphere, hydrosphere, and atmosphere of the Earth. Carbon is the main component of biological compounds as well as major component of many minerals such as limestone. Along with the nitrogen cycle and the water cycle, the carbon cycle comprises a sequence of events that are key to make Earth capable of sustaining life. It describes the movement of carbon as it is recycled and reused throughout the biosphere, as well as long-term processes of carbon sequestration and release from carbon sinks. Carbon sinks in the land and the ocean each currently take up about 1/4 of anthropogenic carbon emissions each year. So how was the life right before humans in power in the scenes? Well, this will bring us back to the beginning of the Holocene epoch, also known as the Age of the Man, which began 12,000 to 11,500 years ago at the close of Paleolithic Ice Age and continues through today, also known as New Beginning because the last ice age had ended and interglacial epoch just began. As Earth entered a warming trend, the glaciers of the late Paleolithic retreated. Tundra gave way to forests. As the climate changed, the very large mammals that had adapted to extreme cold, like mammoth and woolly rhinoceros, became extinct. Humans, once dependent on these mega mammals for much of their food, switched to smaller game and increased their gathering of plant materials to supplement their diets, and right now, unfortunately, have been creating its own mass extinction. So with that, I also want to go a bit back, which will bring us to Pleistocene epoch. It's typically defined as the time period that began about 2.6 million years ago and lasted until about 11,700 years ago. The most recent ice age occurred then, as glaciers covered huge parts of the planet. The Pleistocene climate was marked by repeated glacial cycles in which continental glaciers pushed to the 14th parallel in some places. It is estimated that at maximum glacial extent, 30% of the Earth's surface was covered by ice. In addition, a zone of permafrost stretched southward from the edge of the glacial sheet. A few hundred kilometers in North America and several hundred in Eurasia. The mean annual temperature at the edge of ice was -6 degrees Celsius, and at the edge of permafrost, which was 0 degrees Celsius. So since we talk about permafrost here, I would like to jump into the other interesting part, permafrost, which is a permanently frozen layer below Earth's surface. It consists of soil, gravel, and sand, usually bound together by ice. In Northern Hemisphere, permafrost covers approximately 22.8 million square kilometers, nearly the size of United States, Canada, and China combined. However, that footprint is rapidly shrinking. While global warming is upping temperatures around the world, the Arctic is warming twice as fast as anywhere else, and faster than it has in the past 3 million years ago. And when surface air temperature rise, below ground temperatures do too, thawing permafrost along the way. Scientists estimate there is now 10% less frozen ground in the Northern Hemisphere than there was in the early 20th centuries. One recent study suggests that with every additional 1 degree Celsius of warming, an additional 3.8 million square kilometers of permafrost could eventually disappear. Even if we meet the climate targets laid out during the 2015 in Paris Agreement, the world may still lose more than 6.5 million square kilometers of frozen ground. So in another way, like we touch upon, twice the amount of carbon that is currently present in the atmosphere. Future climate change is expected to reduce its near surface cover by 90% by the end of this century, leading to Thermokarst Lake formation. So this will bring us to our main topic, Thermokarst. Thermokarst is development is one of the most obvious consequences of permafrost degradation. Thermokarst terrain exhibits a pitted relief form from the melting of ground ice. Thermokarst is used widely to describe all processes and landforms that are associated with melting ground ice, but thermokarst or thaw lakes are probably the most well-known features. I also try to put some of the examples from the thermokarst terrain because we always remember thermokarst as the one we see on the left side, but actually any of them can be thermokarst. So thermokarst processes are generally only considered with respect to permafrost terrain, and soil displacement due to melting of seasonal frost is not included. Thermokarst topography and landform are found throughout the permafrost regions, wherever ground ice is exposed or melted. Thermokarst features are uncommon in bedrock areas, but may occur locally in depressions where a sedimentary cover, including ground ice, has accumulated. In addition to direct climate warming and permafrost thaw, thermokarst can be induced by active layer, slope erosion, slumping, soil creep, and deflation, which lead to a thinning of active layer and a new thermal equilibrium. Since the Little Ice Age over, 30% of the permafrost region has been affected by thermokarst subsidence. A new thermokarst terrain is currently forming. A recent thermokarst assessment by another research estimated that some 20% of the northern permafrost region is covered by thermokarst landscapes. So, since we learned that thermokarst has the important portion of the permafrost right now, maybe we can also talk about thermokarst and its relationship with carbon cycle. So thermokarst lakes play a significant role in the current climate by functioning as point sources of greenhouse gases and emissions in comparison with surrounding soils and sediments. Thermokarst lake expansion therefore results in an increase in greenhouse gas emissions. The expansion of thermokarst landscape is accelerated by the physical phenomenon of rapid heat conduction through thawed water bodies, leading to abrupt thaw beneath and around the thermokarst lakes. Model lake sediment temperatures are about 10 degrees Celsius higher than mean annual air temperature, leading to vertical and radial expansion of thermokarst lakes. So this is the one I try to explain here. Therefore, heat conduction in thermokarst lakes significantly contributes to early thaw progression. This early can be imagined as 100 years earlier. However, the heat conduction effects are different for shallow and deeper thermokarst lakes. So shallow, fast ice lakes completely freeze over during winter, whereas deeper floating ice lakes have a year-round unfrozen sediment. Within the Arctic coastal plain of northern Alaska, many fast ice lakes have transitioned to floating ice lakes since the 1980s. This has direct consequences for cumulative heat storage in lake sediments. For floating ice lakes in Alaska, layers of unfrozen ground called thaws form underneath the lakes. Similar observations were made for Siberian thermokarst lakes, where field measurements also showed an increase in thaw deep below lake of 5 to 10 centimeter per year. So the thaw progression is generally rapid in the first years and slows down over time. But overall, thaw lakes facilitate rapid thaw beneath lakes and cause deeper carbon stocks to become bioavailable. Besides the vertical growth, thermokarst lakes also undergo horizontal expansion. The collapse of surrounding Yedoma increases lake surface area, whereas slumping of adjacent sediment introduces organic material into the lake. So since we try to talk about the biodiversity, I want to also touch upon the importance in the biodiversity side as the final part of this topic. So the thermokarst processes not only accelerate thaw, but also stimulate the release of carbon, nitrogen, and other nutrients from deeper permafrost layers. In turn, microbial activity can further accelerate the release of nutrients and greenhouse gases. Thermokarst lakes water are supersaturated with carbon dioxide and methane, indicating a constant input and turnover of terrestrial carbon stocks, which is corroborated by dissolved organic matter signatures. So there is also a small explanation I try to put together, which can be shortly say that the water quality of growing or newly formed lakes is also likely to be increasing affected by changes in the adjacent permafrost landscape as it progressively thaws and degrades. Complex changes in vegetation regimes are also likely to result from the appearance or disappearance of thermokarst lakes. The suite of changes further complicated by the northward movement of vegetation types that will accompany also the climate change. Like appearance and drainage may increasingly affect the traditional practices of the indigenous people in the region as well, particularly where they are used for subsistence, fisheries, or small mammal harvesting. In general, the appearance and disappearance of thermokarst lakes could be used as an indicator of climate warming and the associated effects on permafrost in the northern regions. So maybe you also hear indigenous people and their neighborhood. Actually, yeah, this is the point like I also want to touch. Infrastructure in flat terrain, consolidation of thawed soil leads to subsidence of the ground and undulating topography because the rate and extent of thawing is spatially variable. This variability stems primarily from heterogeneous distribution of ground ice. In sloping terrain, high core water pressures lead to a reduction in effective stress and loss of soil strength, so that slopes may fail. Landslides are common in permafrost terrain that has been burned by forest fire because the resulting change in surface characteristic, not the heat of the fire, raises ground temperatures and leads to permafrost degradation. Thermokarst processes may be problematic for infrastructure and design of construction projects, which modify surface conditions and warm the ground. There are numerous examples of structures that have become unserviceable due to melting of ice. Beneath them. While the thermal effects of artificial surfaces can be modeled, the ground ice distribution at a site is commonly less well known and the source of the most unforeseen incidents. In northern Russia, city buildings are crumbling. In Alaska, roads are turning into roller coasters. When water turns into ice underground, it expands and the ground swells. When water thaws, the ground contacts, which can make it earth crack or cave in, as exemplified by potholes that form in spring. About 35 million people live in permafrost zone in towns, and cities built on top of what was once considered permanently frozen ground. But as that solid ground softens, the infrastructure these communities rely on grows increasingly unstable. So finally, like we also touch about the people who actually live on these vulnerable places, the warming Arctic is driving rapid changes in both natural and built environments. It is challenging the resilience of social and cultural systems, and it's demonstrating that a resilient Arctic is a resilient world. Understanding of infrastructure and community resilience in the changing Arctic is one of the first its kind and draws on the diverse skill sets of not only the scientists, but also the broad range of collaboration communities, partners, and knowledge holders. Data from this effort will inform intergovernmental and international collaboration and identify the types of investments needed to develop innovative engineering solutions with the goal to achieve resilient infrastructure communities in a rapidly changing Arctic. So to conclude, Thermokarst lake dynamics are highly complex and less cyclic than often assumed. For Siberia, it has been reported that thaw leads to initial lake formation and lake area expansion, which is followed by rapid drainage and lake disappearance. Rapid lake drainage can also be observed in Alaska and the Western Canadian Arctic. Due to these dynamic processes, Thermokarst is often considered to have a major impact in the short term. However, its dynamic nature hampers accurate quantification of future Thermokarst lake development, which stresses the need for field data. Data on microbial methane dynamics in Thermokarst lakes are essential to better estimate carbon dioxide to methane emission ratios. These ratios are a main input for current permafrost climate feedback models. Also, major changes in water chemistry and microbiology occur when permafrost thaw results in small Thermokarst water bodies. These small lakes are often not included in global models, but they have a significant contribution to the hydrology and greenhouse gas emissions of the ecosystem. Future greenhouse gas emissions models should therefore aim to include these small water bodies as well. So with that, I want to conclude. I want to finish my presentation with these valuable sentences. We are not stuck in a tragedy of commons. Rather, we are stuck in the belief that we are trapped in such a tragedy of commons, hereby waiting unnecessarily for others to act first. Because, as you may all know, not only proved science or political power can be an obstacle. We actually need a first step from ourselves to inspire the others. So thank you for listening.